Our solar system resembles a grand and enigmatic celestial palace. Among its 8 planets, each one glistens like a brilliant gem, tracing its own predetermined orbit and contributing to the grand symphony of the cosmos. Within this planetary family, Jupiter stands out as the most dazzling presence due to its unparalleled characteristics. Its immense influence extends deeply into the structure and evolution of the solar system, as well as the fate of Earth. Jupiter, a gas giant with a mass that dwarfs the other planets, is approximately 2.5 times more massive than all the other planets combined. This astonishing mass not only solidifies Jupiter's dominant position among the solar system's planets, but also establishes its critical role in the cosmic arena. Its enormous mass endows Jupiter with a tremendously powerful gravitational field, functioning like an invisible net that stretches across the vastness of the solar system. This field exerts a formidable force on surrounding celestial bodies, from microscopic cosmic dust to larger asteroids and comets, attracting and controlling them within its sphere of influence. For Earth, Jupiter's presence is of crucial importance. The giant planet's powerful gravitational field creates a robust shield on the outer edge of Earth's orbit. This shield acts like a vigilant guardian, blocking potential threats from small celestial bodies that might pose a risk to Earth. In the early stages of the solar system's formation, the interstellar space was filled with diverse materials and celestial bodies of varying sizes and shapes. These materials collided and merged under the force of gravity, eventually forming the planets and other celestial bodies we observe today. During this chaotic process, Earth was at risk of frequent impacts from these cosmic projectiles. However, as Jupiter formed and its gravitational field grew stronger, many potential impactors that could have struck Earth were captured by Jupiter's gravity. These bodies were either bound into orbit around Jupiter as moons or torn apart and incorporated into Jupiter's atmosphere. This gravitational shield significantly reduced the frequency and intensity of impacts on Earth, creating a relatively stable and safe environment conducive to the emergence and evolution of life. Thus, Jupiter is rightly celebrated as Earth's protector. In the long history of human exploration of the cosmos, the year 1994 stands out as particularly significant. During this year, humanity witnessed a dramatic and awe-inspiring celestial collision event that underscored Jupiter's immense gravity and its crucial role in the solar system. This event involved the intense collision of comet Shoemaker-Levy 9 with Jupiter. Originally a solitary traveller in the vast universe, Shoemaker-Levy 9 was formed on the distant edge of the solar system from ice, dust, and gases. Over many years, it travelled along its orbit, away from the warmth and light of the Sun, immersed in the depths and silence of space. Shoemaker-Levy 9 had a cometary nucleus about 5 kilometres long, composed of rock, ice, and organic material, covered by a thin layer of volatile substances. As the comet approached the Sun, these substances evaporated, forming the comet's tail and coma, giving it its characteristic appearance. In the late 1960s or early 1970s, Shoemaker-Levy 9's trajectory underwent a significant change as it gradually approached Jupiter. Entering Jupiter's powerful gravitational field, the comet became trapped, transforming from a free-roaming celestial traveller into a captive within Jupiter's influence. The comet's orbit around Jupiter took on a highly elliptical shape, causing it to vary in distance from the planet, sometimes coming close and other times moving away. Over time, the effects of Jupiter's gravity and complex celestial dynamics caused Shoemaker-Levy 9's orbit to gradually decay, bringing it closer to Jupiter. On July 7, 1992, a pivotal moment occurred in the fate of Shoemaker-Levy 9. By this date, the comet had come within approximately 40,000 kilometres of Jupiter's cloud tops. At this distance, the tidal forces exerted by Jupiter became extremely strong. According to astrophysical theories, When the distance between a small body and a larger body falls below a critical threshold, the tidal forces can exceed the small body's own gravitational binding forces, leading to deformation, stretching, and even fragmentation of the small body. In this case, Shoemaker-Levy 9 crossed Jupiter's Roche limit and was torn apart by the planet's immense tidal forces into 21 fragments of varying sizes and shapes. These fragments continued to orbit Jupiter, forming a unique ring system composed of cometary debris. Their orbits, speeds, and directions were precisely controlled by Jupiter's gravity. As a result, a new but short-lived cosmic journey began. To facilitate scientific study and observation of these fragments, astronomers assigned them designations using letters from A to W, avoiding the letters 1 and O to prevent confusion with the numbers 1 and 0. The fragments varied in size, shape, and mass, reflecting the complex physical processes and forces involved in their fragmentation. Among these fragments, the one designated D was the largest, with a diameter of about 2 kilometers. Due to its significant mass and size, it was expected to release tremendous energy and material during subsequent collisions. In addition to the large fragment, those designated L and K also had diameters exceeding 1 kilometer and possessed substantial mass and energy. Together with smaller fragments, they formed a perilous and unknown array of debris orbiting Jupiter. After being shattered, the fragments continued to orbit Jupiter, but their orbits gradually decreased in height due to the ongoing influence of Jupiter's gravity and the dissipation of orbital energy. Astronomers, using precise measurements and advanced celestial mechanics theories, predicted that by the summer of 1994, the fragments' orbits would fall below Jupiter's radius, leading to inevitable, direct collisions with the planet's surface or atmosphere. This prediction meant that a cosmic-scale collision event was imminent, poised to release immense energy and material and profoundly impact Jupiter's atmosphere, surface, and internal structure, providing a rare opportunity for direct observation and study of such collisions. On July 16, 1994, the day destined to be recorded in the annals of astronomical history, Shoemaker-Levy 9's fragments began impacting Jupiter's southern hemisphere, initiating a breathtaking cosmic collision journey. These fragments, travelling at speeds up to 21,000 kilometers per hour, struck Jupiter's surface with extraordinary force, generating intense impacts and explosions. In the instant of collision, the enormous kinetic energy of the fragments was rapidly converted into thermal energy, light, and other forms of energy, releasing unimaginable power and brightness. The impacts created massive fireballs in Jupiter's atmosphere, demonstrating the immense scale and impact of this extraordinary cosmic event. The intense friction and collisions caused gases to be rapidly heated to extremely high temperatures, resulting in powerful luminous and thermal phenomena. Each fireball represents a massive release of energy and interaction of matter, involving complex physical processes and chemical reactions. Inside these fireballs, the extreme temperatures and pressures excite and ionize atoms and molecules, creating a plasma state that generates intense electromagnetic radiation and particle emissions. The collision process lasted over 5 days, turning Jupiter's southern hemisphere into a colossal cosmic battlefield, continuously staging dramatic impact events. Each collision left deep and lasting marks on Jupiter's atmosphere and surface, altering the local physical and chemical conditions. These impacts not only released vast amounts of energy, but also ejected substantial quantities of cometary material into Jupiter's atmosphere, including ice, rock, dust, gases, and various organic compounds. These materials interacted with Jupiter's atmosphere and surface, forming new compounds and structures. After this series of impacts, Jupiter's surface bore a series of massive scars, which are permanent evidence of the cosmic energy release and material interactions. Among these, the scar created by the largest fragment was the most prominent. Data measurements indicated this scar had a diameter of approximately 12,000 kilometers, nearly equivalent to Earth's diameter. This enormous scar was caused by the massive fragment releasing tremendous energy and material upon striking Jupiter's surface, creating a powerful explosion and impact zone. Within this zone, Jupiter's atmosphere and surface were instantaneously heated, evaporated, and ejected, forming a giant cavity and depression. Over time, this cavity and depression gradually filled in and repaired with surrounding materials, but still left a significant mark, serving as a landmark for this collision event. In addition to the major scar from the giant fragment, other fragments left varying sizes and shapes of marks on Jupiter's surface. These scars collectively formed a complex impact pattern, reflecting the interactions and results of Shoemaker-Levy 9's fragments with Jupiter. Due to human preparation and scientific prediction, we were able to observe and record this event using advanced observation equipment and technologies such as the Galileo spacecraft, the Hubble Space Telescope, and various ground-based observation instruments. The Galileo spacecraft, launched by NASA, was dedicated to exploring Jupiter and its satellite system. During the Shoemaker-Levy 9 impact, it was positioned near Jupiter's orbit, providing high-resolution data and images of the event. The Hubble Space Telescope, a significant space-based observational tool, captured stunning moments and details of the collision process, including fireballs in Jupiter's atmosphere, ejected material, and surface scars. Ground-based optical, radio, and infrared telescopes also observed and recorded the event from different perspectives and wavelengths. The combined efforts of space and ground-based observatories built a comprehensive observational system, allowing a detailed understanding of the collision event. Astronomers, using advanced physical theories and models to analyze these observations, estimated the total energy released in the event to be about 40 trillion tons. This energy magnitude is comparable to over 20 Hiroshima atomic bombs. To grasp this scale more intuitively, we can compare it with Hiroshima's atomic bomb explosion, which released about 15,000 tons of TNT equivalent energy. The Shoemaker-Levy 9 collision released energy equivalent to about 20 billion Hiroshima bombs. This figure underscores the enormous destructive power and energy release of the impact event. From the energy release perspective, the Shoemaker-Levy 9 collision was an exceptionally rare and violent celestial event in the solar system. The energy released not only had a profound impact on Jupiter's atmosphere, surface, and internal structure, but also caused significant disturbances and changes in Jupiter's surrounding space environment and magnetic field. For Earth, such a collision would have catastrophic consequences, affecting the atmosphere, ecosystem, geological structure, and life itself. Historical major impact events on Earth, like the asteroid impact that led to the extinction of dinosaurs around 65 million years ago, resulted in a massive impact crater and triggered global disasters such as strong earthquakes, tsunamis, volcanic eruptions, and a nuclear winter. If Shoemaker-Levy 9's fragments had struck Earth, the resulting energy release and environmental impact would have far exceeded that of the dinosaur extinction asteroid, likely causing massive life extinction and ecosystem collapse. Fortunately, Jupiter's presence shields Earth from many potential threats. It is worth noting that the 1994 collision was not the only time humans witnessed Jupiter's powerful gravitational capture and impact capabilities. With advancing observational technologies, we have observed multiple small celestial impacts on Jupiter over the years. Though smaller in scale compared to the 1994 event, these occurrences demonstrate Jupiter's significant role and position in the solar system. Recent observations and analyses show that Jupiter experiences 4 to 25 observable small celestial impacts annually. However, due to limitations in observational equipment, angles, and the nature of the impacts, many smaller events remain undetected. Theoretical models and data suggest that Jupiter may experience up to 650 impacts per year. Although these events appear as brief flashes from Earth, They represent intense and complex processes of energy release and material interactions. For instance, on September 13, 2021, astronomers captured a small celestial impact on Jupiter. While this impact was relatively minor, it provided valuable insights into Jupiter's interactions with small celestial bodies. The brief flashes observed from Earth reflect the massive energy releases and material interactions occurring on Jupiter. If similar events happened on Earth, the consequences would be catastrophic. Thus, over billions of years, Jupiter has likely captured and destroyed numerous small celestial bodies that might have otherwise posed a threat to Earth. Jupiter's strong gravitational field has acted as a protective shield, preventing potential impacts with Earth and ensuring the safety of life on our planet. In summary, Jupiter's role as a protector of Earth is undeniable. In the vast and mysterious universe, we should appreciate this cosmic guardian's protection and continue to enhance our understanding of space through observation and research. Exploring Jupiter and other celestial bodies to better comprehend our cosmic environment and the significance of our existence.